This is Bailey Hill, and this is my Statistics Module 3 presentation. So I want to start off going over the GLM, or the General Linear Model. The GLM can take multiple forms, so multiple regression and correlation, MRC, and analysis of variance, which is ANOVA. It's called the GLM because it generalizes to multiple, more specific models. It restricts the model to an additive plus and can be considered linear and is model-based. In going over our model equation here, y is the dependent variable predicted by x, and it's imperfectly predicted. B0 here is the intercept of the regression line with the y-axis, or the value of y if x equals 0. B is the weight assigned the predictors and the weight that provides the best fit, and then epsilon is the residual as well. So first I'm going to go over MRC, which is measure association. The two different parts of parameter estimation and hypothesis testing, and the purpose of MRC is to have more predictor specification, main effects interactions, and rectilinear curvilinear relations. So I did one analysis software MRC here, and here's our scatter plot. This is analysis of variables x1, x2, and x3. There seem to be 3 extreme outliers in this case after looking at data, and it violates the assumption of MRC that the relationship between x and y are linear. Going into the SPSS statistics, our parameters and hypothesis testing. Again, I ran the MRC here of variables x1, x2, and x3. In this, our Durbin-Watson statistics should be close to 2. Ours is 2.076 here, so it doesn't violate the assumption of independent residuals. And then also our these are not all significant because our p-values are greater than 0.05, even though x1 is close here. Our standard error is around 24%, so 24% of the variability of x1, of y1, and they help predict y1 as well. Our VIF values are acceptable because they're less than 4, so over here, these are all less than 4. Our betas are fine because they're between -1 and 1 right here, and then there are no problems with linearity as well. Since SPSS automatically issues an ANOVA for our data here, I'm not going to discuss it because we're going to be running an ANOVA later, so I'll go ahead and skip over that. So here are outliers. So our mean leverage value is 0.1, so we'll use 0.2 and 0.3 to see if there are influential cases in the data set. And I noticed that there's 3 numbers that are above 0.2 that will be taken out when I rerun the analysis. So I went ahead and ran a second analysis while removing the 3 outliers here, looking at our scatter plot. According to the Cortina rating, these extreme outlying values can have a large impact on results, but according to him, we need to be careful to analyze the data before we make decisions on removing outliers. So I analyzed the data in our first software analysis, realized that we needed to remove 3 cases, and then after looking at it again, there doesn't seem to be any more extreme outliers, but this does violate the assumption that variance is constant for all values of x, which means the plot is heteroscedastic. So if we're looking at this plot, we can see if we put our line directly through, they're not matching on either side, so there's a lot of high heteroscedasticity in this plot. If we're going to look at our second analysis and our parameters and hypothesis testing, so our Durbin-Watson should be close to 2. Ours is 1 here, so this violates the assumption of independent residuals. Our VIF values should still be less than 4, which they are, so there's no problem with multilinearity. All of our sig values are above 0.05, which makes them not significant, and we've failed to reject the null. Moving on to our leverage and outliers. So we can multiply our mean by 2, which will remove influential cases above 0.16, which are 3 more outliers. The results remain pretty similar to the first analysis, though, and removing more numbers from an already small data set is not good. So I'll go ahead and move on to coefficients, because if we keep removing outlying data, we're just going to have meaningless statistics. So in our coefficients here, all of our sig values are above 0.05, which they're not significant. Cook's D, no values exceed -1 or +1, so no observations need to be excluded from that. Our betas are all between -1 and 1, which is acceptable. x1, x2, and x3 account for around 21% of variance here for y1, and so 24% in analysis 1. So moving on into our residual statistics, so our mean error of residual should equal 0, so there's no violations in this data. In the histogram and PP plot, so these residuals should be normally distributed. This histogram is close to a normal distribution, but is slightly skewed, so it's not completely typical. The PP plot shows the data set is pretty normal as it follows this line here. There's a few that go slightly off, but for the most part it follows the line very well. In our assumptions of linearity, x1 and x2 are negatively correlated, which doesn't violate the assumption of linearity. ANOVA also requires linearity, which we'll be getting to soon. Our skewness value here is negative 0.5059, and it should be between negative 1 and 1, which is normal. Negative 1 and 1 it limits for variables that are highly skewed. This means that this has a moderate skew because it's between negative 0.5 and 0.5. Kurtosis is negative 0.813 right here. And it should be between negative 2 and 2, so this can be concluded that's a fairly normal distribution. So moving on into our analysis of variance, so I'll be doing an ANOVA next. Although they're slightly different, both tests are concerned with understanding variance, obviously. So the sample size in this condition is not equal, so this makes it an unbalanced test and violates the identical assumptions. Moving on, this is Levine's test of equality of error variance. So if we look in the SIG column, and it is greater than 0.05, we can conclude there's no significant difference. This means we've not violated the assumption of equal variance. And then our test between subject effects under our SIG values, none are significant because they're all greater than 0.05, so we can fail to reject the null. And then after looking at the F table, I saw the critical value to be 4.26. None of the F values are significant, as obtained value is 0.029. So we can fail to reject the null in this case as well. For F2, right here, the critical value is 3.44, so our obtained F value is 2.308, which is also not significant, so we can fail to reject the null again. Moving on to the next slide, so our scatter plot here. So this is the same scatter plot that I used for regression, but could also be used to test for homoscedasticity. The x-axis is predicted and y is residual. If the distances from the residual mean are similar, it has high homoscedasticity, but as we can see from our plot here, although some of these look like they're pretty well matched on either side, there's a lot that seem to be outliers here and here, as well as here. So there's a lot of heteroscedasticity in this plot. King notes in his article that dichotomous dependent variables can be the cause for heteroscedasticity as well. This is similar to our MRC, as both assume homoscedasticity. Next, I wanted to go over my MRC hand calculations. So as you can see, I ran this right over here, or y in this case is y equals 5.514 minus 0.17x, and then our ANOVA hand calculation is here, so here and here. I want to say thank you for a really intriguing and fun class, and I will look forward to seeing you again in regression. Thanks.